Hello and welcome to this course on privacy enabling techniques. So we shall be dealing with several topics which expand on various aspects of cryptography and security, and try to see that how we can make our data confidential and private while also allowing computations on that. So this will be a 12-week course and we shall be dealing with several aspects on this topic. But before we get started, let's start with on a lighter note with a game. Suppose as a teacher, we are curious to know that how was our class, and I ask the students that can you give me a response by saying 1 if the class was good and 0 if the class was not so up to the mark. So as a student, obviously, right, you might be hesitant to disclose, and professors like asking for students' feedback is therefore always a sort of tricky question. So on one hand, you as a student would like to kind of maintain your privacy. You would like to kind of ensure that I as a teacher I'm not able to ascertain what individually every student says. But collectively, as a teacher, right, I should be still able to kind of gather statistics about how the class was, because a good feedback is definitely very important to improve the quality of the lecture. So imagine that we try to kind of come up with a solution to this conundrum and try to come up with like a sort of like a strategy to address this problem. Here is a very simple strategy that one can try to adopt. So the PETS teacher, for example, can come up with this suggestion that each of you are provided an unbiased coin, which basically means that the probability of a head and a tail is exactly half or around half, and you toss it, and based upon that you answer. So the strategy to answer is as follows: like if it is a head, then you provide me a 1 for a good class, and if it's a 0, then essentially, right, the class was not so good. On the other hand, basically, like in this context, right, if it is a head, you actually provide me a response to the question, which was basically whether my class was good or not so good. On the other hand, if it is a tail, then you provide me a 1 if you are born in the first half of the year and 0 otherwise. So you see that this is an answer that you are giving which is completely unrelated to the question, right? So as you can understand that like if I just see a 1 and a 0, I do not have a mechanism of understanding whether you responded to the question that whether my class was good or bad, because you can basically like pretty much take the path 2, because like your coin toss resulted in a tail, and you can provide a response which is completely unrelated to the question. So you see that your privacy is like better tackled in this manner rather than like I bluntly seeing your response. On the other hand, I will also try to argue with you, and that's not too difficult to see that you from the overall statistics, like the overall number of ones that I accumulate, you should be able to gather a reasonable answer or like response to the question or the statistic that I want to gather. How can you do that? It is as follows. So this is the like the first point that I mentioned, that the students can be happy because professor, when he sees a 0 or 1, does not really know the real answer, as it can be because of the tail outcome of the coin, which occurs with a probability of half. So this part is quite easy. We see that the students can be happy and the privacy is reasonably maintained. But the more interesting question is that from this accumulation of ones and zeros, how do I gather a kind of a reasonable estimation of the statistic that I want to gather? So let's see how we can do that. How do we really know the actual answer? So imagine that suppose like you have got a class population of 200 students, and therefore assuming that your coin is a like a reasonably good coin with a probability of head being half and tail being half, I can pretty much assume that 100 of them is expected to result in heads and 100 would probably result in tails. So therefore what I can pretty much answer and also observe that if you observe the second question, whether you are born in the first half of the year or the second half of the year, also has got a probability of half, right? So therefore, of the remaining 100, we can expect around 50 being ones, because that probability is also half. So therefore, what can be my strategy? Suppose imagine that I observe that there are n ones, right? That I observe there are n number of ones, and it could be some number that I observe as a result of this eventual accumulation of the statistic. So then what I can estimate, or the way to estimate the actual the result that I want to kind of compute is just subtracting 50 out of n, because this number or this value that I get is actually getting gathered from the response to the first question, which is the actual question for which I want the answer. So this number, from here I can calculate the average, and I can pretty much have a reasonable estimation of the average number of people who are going in favor of the class, and hence as a natural outcome, how many of them are not in favor of the class. So therefore, I am able to gather the statistic. Essentially, that is very important for improving the class. But what is the individual response? That I have got no clue. If I see a 1, I do not know whether the 1 is a response to the first question or whether that is an outcome of the second question. So you see that this is a very simple strategy, but at the same time, later on we will see it brings out a very interesting idea, an important idea in the overall gamut of PETS techniques. But there are very interesting ways of coming up with solutions for PETS questions. So you can respect the privacy of individuals, but still can do computations to gather vital and important statistic. So therefore, we shall deal with much more things in the course. So now the question that probably can come to our mind is that why is privacy so important, and why do we at all study a course on PETS? So we know that we are dealing with several applications that are embedded, and we are every day using several applications. And often there is a term which says it's a free app economy, which means that the app is free and everything looks great. So there is a famous saying that if the service is free, then who is the product? I as an individual am the product. Now when I say that you are the product or I am the product, then that basically means that our data is essentially precious. Okay, and while you see on the surface that the free app provides several facilities, but under the surface it actually performs several computations, and several, very, very important and personal information, like your, personal, for example, photos, your own medical data, your own various, characteristics, liking, dislikings, political bias, and so on, can get, sort of discovered to the external agencies. Now, this is something that we do not want as individuals, because we want to protect our privacies, but at the same time, people should be able to kind of provide services, and we should be able to kind of make our day-to-day life better by using these technologies. So this is a very interesting riddle, right? How do we really provide these services, but without divulging our own personal information? So this course deals with techniques or computational techniques, technologies which kind of address this important concern. So what we'll be covering in this course are several important aspects. So for example, one of the important things that we will try to study is a technique which is called as homomorphic encryption. We will see theory, construction, and practice of this technology. So what homomorphic encryption means as a very broad overview is that while the data is encrypted, because as a natural strategy to protect your information, to make your data confidential, you would probably try to kind of encrypt your information. But the moment you make your data encrypted, they are not usable. You cannot perform computations on that. Imagine that you want to develop a large language model like ChatGPT and so on. It is very often giving you very excellent responses, but they are also working on your own personal data. So what homomorphic encryption kind of says or suggests is that it develops a technology wherein the data is encrypted and therefore it is hidden to the external world, but still you should be able to kind of perform operations on them, computations on them, and give you responses or results which looks completely gibberish to the external world, as you can see on the right on the below illustration, that the ChatGPT, when it is kind of protected by say an envelope of homomorphism, then it is giving you a result, but the result is not understood to the external world. But you, since you have your own decryption key, you can now decrypt and get the result. So this is a a very interesting idea and technology which often is also referred to as the holy grail of modern day computation, which we will try to take a deep look into the class. Likewise, We also can, we will deal with the technique which is called as multi-party computation, which basically means that your data is supposed distributed across various networks, various endpoints, and you want to do computations on them without giving the individual information. So on one hand, while homomorphic encryption, which we have probably studied, will be studying before, is a very computationally heavy operation, multi-party computation we will see is kind of the other side of the spectrum, which basically does very little computations but do lot of communications. And using that, you can also come up with very nice privacy preserving solutions which you can apply to, like solving interesting problems like votings, elections, and so on. So we'll try to see, like how you can really perform these kind of techniques in a privacy preserving manner. And, like as a natural extension of this, you can also develop applications as interesting as privacy preserving machine learning. So now next we will also try to take a look at another very interesting piece or technique on in this PETS course, which are called as zero knowledge proofs. So for example, suppose I have a secret and I want to give a proof of that. Now using that proof, you can also give a proof or transfer that proof to a third party. Now as a very like unique idea of zero knowledge proofs, it comes up with theories and applications of the same, where the idea is that I will give you a proof, but using that proof, you cannot give or transfer that proof to a third person. So you can verify the proof, but you do not know the secret which is based on which I am developing the proof. So there are also very interesting applications of this in the context of electronic caches and blockchains, and we will try to see the theory and applications of the zero knowledge proofs, or ZKPs as they're often referred to. Now, so while we are talking about like mathematical tools which we will be studying so far, we will try to take also a look at another aspect of PETS techniques which are more based on architectures. So modern day computer systems, like when they range from like less resource endpoints like embedded systems to more resourceful servers, and like being the laptops being at the middle point, also offer several trusted architectures under which you can also do your privacy computations. So for example, there are like solutions for ARM from Intel, from AMD, and several like companies which tries to give us like with techniques of trusted architectures, which are also a very important piece in the gamut of PETS techniques. And there is a huge market that is evolving. It is expected that around by 2030, the market of PETS of trusted architectures will probably reach around 4.3 billions. So they are also extensively being deployed in modern clouds, and often like in spite of several cryptographic techniques being developed, remains as a very important piece where technology comes to solve the problem of PETS. So we'll try to take a very quick look at some of these architectures and try to get a flavor of what TEAs or trusted execution environments stand for, and how they are operating in this context. So the takeaway from this course, like without going into much more details today, I'll rather say that this is a 12-week course, around 2.5 hours of lectures per week. There will be assignments which we will try to kind of regularly upgrade and try to see that the lectures that we are doing is really getting transferred to you properly. And we want to develop a know-how about the state-of-the-art techniques to ensure privacy. We want to and the end point, right, should be that like we should be able to contribute to the ecosystem community with better use cases. We should be able to build and deploy practical applications using this know-how. So this is a kind of word cloud that you can later on see, where we try to give you some like important terminologies that will evolve in the course, and pretty much they give you the syllabus of the course. And I'm not really like spelling them out. You can take a look at the word cloud later on. So with this, I would like to stop today, and I'm very excited to offer this course, and I hope that this course will be useful to not only high school, for example, like students at their third year or fourth year level, but also to researchers like PhD students, master students, and also people who are working in the industry and working in this very important topic of privacy enabling techniques. So with this, I would like to say thank you, and looking forward to see you in the course. Thank you.